Study Section 4. Our Models. Introduction. You should have studied through the concept of conditional probability and proved the twin concept Bayes theorem and total probability in the previous study session. Here, in Study Section 4, you will learn how to discuss issues of counting, partitioning, selection, and distribution of objects. Learning outcomes for Study Section 4. At the end of these study sessions, you should be able to state the fundamental principles of counting, define the Stieltjes number of the second kind, state the Stieltjes identity, apply 1 to 4 in solving related problems, sampling with and without replacement. Fundamental principle of counting. Consider a finite sequence of decisions. Suppose the number of choices for each individual decision is independent of decisions made previously in the sequence. Then, the number of ways to make the whole sequence of decisions is the product of these numbers of choices, that is, n factorial. Example 1. The number of four-letter words that can be formed by rearranging the letters in the word plan is 4 factorial is equal to 24. Definition 1. The number of ordered selections of R elements chosen from an n-element set is P of n R in bracket. P of n R is equal to n factorial over n minus R in bracket factorial is equal to R factorial combination n R factorial combination nr. Example 2. Suppose 6 members of Adiola School's Parent-Teachers Association meet to select a 3-member delegation to represent the association at a statewide convention. If the laws stipulate that each delegation be consisted of a delegate, a first alternate, and a second alternate, how many ways can the 6 members comply from among themselves? Solution. P of 6, 3 is equal to 120 ways, or 3 factorial combination 6 of 3 is equal to 120 ways. Definition 2. The number of ways of making a sequence of R decisions, each of which has n choices, is n raised to power R if order matters and the selection is replacement. Definition 3. The number of different ways to choose R things from n things with replacement if order does not matter is C into bracket R plus n minus 1 R. Example 3. How many different 3-letter words can be produced using the alphabet Alexi? Solution. Since there are no restrictions on the number of times a letter can be used, 5 raised to power 3 is equal to 125. Such words can be formed. Example 4. At a fundraising luncheon, each of 50 patrons is given a numbered ticket, while its duplicate is placed in a bowl from which prize-winning numbers will be drawn. If the prizes are 50 naira, 100 naira, and 150 naira, how many outcomes are possible assuming that winning tickets are not returned to the bowl? If the prizes are the same, say 70 naira, each for the 3 prizes, how many outcomes are possible assuming that winning tickets are not returned to the bowl? If the winning tickets are returned to the bowl, how many outcomes are possible when the prizes are as in 1 and 2 respectively? Solution. P of 50 and 3 in bracket is equal to 117,600 different outcomes are possible. Since the prizes are the same, then order is not important, implying that there are C 50, 3 in bracket is equal to 19,600 different possible outcomes. A. Different prizes with replacement order matters. 50 raised to power 3 is equal to 125,000. B. Same prizes with replacement order does not matter. C. 3 plus 50 minus 1, 3 in bracket is equal to 22,100. Note, in choosing with replacement, elements may be chosen more than once. If order does not matter, then we are only concerned with the multiplicity with which each element is chosen. Table 5.1 summarizes the 4 scenarios that we have considered. Stealing numbers, second kind. Definition 4. Let S be a set. A partition of S is an ordered collection of pairwise, disjoint, non-empty subsets of S whose union is all of S. The subsets of a partition are called blocks. For S is equal to A1 union A2 union A3 union AK to be a partition of S. AI intersection AJ is equal to empty set whenever AI intersection AJ is equal to empty whenever I is not equal to J. AJ is not equal to empty 1 less than or equal to J less than or equal to K. Two partitions are equal if and only if they have the same blocks. For instance, 1 union 2 3, 1 union 3 2, 2 3, union 1 and 3 2, union 1 are 4 different looking ways of writing the same two-block partition of S is equal to 1, 2, 3. The other partition of S is equal to 1, 2, 3 are 1 union 2 union 3, 3 blocks. 1, 2 union 3, 2 blocks. 1, 3 union 2, 2 blocks. 1, 2, 3, 1 block. Thus, S has a total of 5 different partitions made up of 1 union 2, 3, 1 union 3, 2, 2, 3 union 1 and 3, 2 union 1. 1 union 2 union 3, 1, 2 union 3, 1, 3 union 2, 1, 2, 3. Definition 5. The number partitions of 1, 2, 3 m into n blocks is denoted by Smn in bracket, and this is known as the Stirling number of the second kind. Note, Smn in bracket is equal to 0 if n is less than 1 or n is greater than m. Also, S into bracket m1 is equal to 1 is equal to S into bracket mm. This is because there is just one way to partition 1, 2, 3 m into a single block, and 1 union 2 union 3 union m is the unique and ordered way of expressing 1, 2, 3 m as the disjoint union of m non-empty subsets. Stirling's identity. For any two positive integers m and r factorial S into bracket mr is equal to, therefore SMR in bracket is equal to, example 5, x4 1 in bracket is equal to 1 is equal to 7. Example 5, s4 1 in bracket is equal to 1. s4 2 in bracket is equal to 7. s4 3 in bracket is equal to 6. s4 4 in bracket is equal to 1. Application of Stirling's number of the second kind to distribution of objects into horns. We are interested in the question in how many different ways can m balls be distributed among n horns. We are going to answer this question by considering whether the balls and horns are labeled or not, and whether a particular horn can be left empty. We will consider 4 variations. Variation 1. In how many ways can m labeled balls be distributed among n unlabeled horns if no horn is left empty? This is the same as in how many ways can the set 1, 2, 3M be partitioned into n blocks? This is S, M, N in bracket. Example 6. In how many ways can 4 labeled balls be distributed among 2 unlabeled urns if no urn is left empty? Solution: S 4, 2 in bracket is equal to 7. That is, if the balls are labeled 1, 2, 3, 4, then the 7 possibilities are, because the urns are unlabeled, is equal to etc. Variation 2. In how many ways can M labeled balls be distributed among n unlabeled urns? Solution: this is SM1 in bracket plus SM2 plus SMN. This is the same as finding the number of ways in which 1, 2M can be partitioned into n of fewer blocks, since it is no longer a requirement that no urn be left empty. Example 7. The number of ways to distribute 4 labeled balls among 2 unlabeled urns is, that is equal to variation 3. In how many ways can M labeled balls be distributed among n labeled urns? This is n raised to power m. Example 8. 5 labeled balls can be distributed among 3 labeled urns in 3 raised to power 5, which is equal to 243 ways. Variation 4. In how many ways can M labeled balls be distributed among n labeled urns if no urn is left empty? This is n factorial Smn in bracket. There are Smn ways to distribute M labeled balls among n unlabeled urns using variation 1. After the distribution of the balls, there are n factorial ways to label the urns. By the fundamental principle of counting, the answer is n factorial Smn in bracket. Example 9. In how many ways can 5 labeled balls be distributed among 3 labeled urns if no urn is left empty? Solution: 3 factorial S53 in bracket. Summary of study section 4. In these study sessions, you have learned about 1. The concept of sampling with and without replacement. 2. Suppose the number of choices for each individual decision is independent of decisions made previously in the sequence. Then, the number of ways to make the whole sequence of decisions is the product of these numbers of choices, that is, n factorial. This is known as the fundamental principle of counting. 3. Sterling number of the second kind is the number partitions of 1, 2, 3, m into n blocks, and it is denoted by S, Mn in bracket. 4. Sterling's identity is defined as application of Sterling's number of the second kind to distribution of objects into urns. This is the end of study section 4. Thanks for listening.